Civil Engineering Department, again with CIVL202 Statics, this time talking about Learning Objective 3.3, the identification of 2 and 3/4 members. Again, we are still working within statics, and so today is the best day to learn statics. Additionally, we're still talking about rigid body equilibrium, so we're expanding upon the work that we did last time talking about frames and machines. So we had several examples here of the mailbag and the ironing board and the backhoe. Now, when we talk about 2 and 3/4 members, what we're doing is we're saying there are some simplifying assumptions we can make about these multi-force members. So last time we defined frames and machines as being pin connected with no more than 2 members at each pin, and when we analyze them, we pull the pins and take the thing apart, drawing equal and opposite forces at each pin location, at the joint, the internal forces at the joint that we'd exposed by pulling the pins. Now, when we do that, we are going to find that sometimes members have a little bit less going on that maybe it requires a full free body diagram. And in fact, in our example problems that we'll work together in class, my hope is that you'll see that develop out and flesh out and see where those things can be. In this case, we'll just jump straight to the definition of 2/4 and 3/4 members. So when we talk about a 2/4 member, 2/4 member, we're discussing members that are applied only at, members that have forces applied at only 2 points. So we have forces at only 2 points. So for example, if we have some member, and it doesn't have to be the ends, but it could be the ends, we might have a set of forces acting on the ends like so and like so. Any number of forces acting on the ends. But the forces are applied at 2 locations. And because it's applied at 2 locations, it is a 2/4 member. Now, the cool thing about a 2/4 member, if we can spot a member with forces applied at only 2 locations, is it turns out that those forces are going to be equal in magnitude, opposite in direction, and pointed along the line of action between those 2 points. So I've got a nice little member here. Nice little axe handle to work with. And the idea is that if I have a pin connection over here with my flat hand, if I'm going to load it, I can apply a load in compression and I can apply a load in tension. But if I try to apply any load that is perpendicular to the member is going to actually rotate, right? So it's no longer in equilibrium. So in order for it to be in equilibrium, it either has to be in compression or in tension. That's all we get. And because it's a 2/4 member, if it's out of alignment and I pull on it, it's going to pull into alignment, right? As I pull. And so with a 2/4 member, it's either in compression or tension because we're applying the loads at only 2 locations. And so if we look at that, all of that complex loading at those 2 locations is going to be in tension or compression. Now we'll draw this tension. We'll assume that to be positive. That will matter a lot to us in our next lecture on internal forces. But for the moment, we'll just draw it in tension, pulling in the 2 places. And so these are going to be equal in magnitude, opposite in direction, and along the line between the 2 points. And so we see here where my magnitude's equal, so I could just call this F and this F. My arrows are pointed in opposite directions, so that's a nice thing. And they're acting along this line of action. So that looks pretty good. I like it. Now, we analyzed that little mail hook, or we broke it down into our free body diagrams from last time. If we just look at this diagram, can we see a member that is a 2/4 member? Hopefully you're seeing that I'm going to have forces at each pin, right? And so if I look at member A, B, C, It's got forces at pin C, at pin B, and at pin A, as well as a moment at A. So that's not a two-force member. Member CDE got forces at pin C, forces at pin D, and out there at the weight at E. Again, 3 locations, not a two-force member. But member BD has forces applied at only 2 locations. And so if we pull the pin and we pull that member out, we could make this claim that instead of this complicated loading down here, I'm going to clean this up a little bit and we're going to simplify that loading. And that means I have to know where my eraser is. Okay. We're not simplifying it. We're just making some assumptions. If you look in your textbook, you can see the proof for this. Hopefully we'll prove it in class together. The thing to say is that if you can't identify a 3-force or 2-force member, that's okay, because when you do your equations of equilibrium, it will actually work out that way. And so if I look at this member BD down here, because it's 2-force, I can assume positive intention, meaning that I'm going to have a force equal in magnitude, opposite in direction, acting at both ends. So this will be FBD, and the same magnitude down here, FBD. Very cool. Acting along the line of action between the two, which means that I don't really need to do any equations of equilibrium for this. I've already done it by virtue of using my definition of a 2-force member. Now, when I've pulled my pins, I'll need to draw the forces equal in magnitude, opposite in direction at the other pin locations. So up here, this will be pulling, because I assumed it was in tension, F, B, D. So pull the pin. Now those two are equal in magnitude, opposite in direction. Right there, equal in magnitude, opposite direction. I'll need the same thing over here, and so I'll have a force acting in a known direction, F, B, D. So this would be point B, this is point D. And that really takes away a set of equations, simplifies our unknowns. Well, there's just one unknown happening in that 2-force member now. Now that brings us to our second category, which would be 3-force members. 3-force members. And these, unsurprisingly, have forces at only 3 points. Forces at only 3 points. And it turns out that if we have forces only at 3 points, we have one of 2 scenarios going on. Either all of the forces are parallel. All forces parallel. So that would mean I'd have a member with forces applied at 3 locations. Forces, 3-force member. And those forces would all have to be parallel. You see how they're all parallel to be in equilibrium? So all parallel. Or we can say that all forces are concurrent. What did it mean for our forces to be concurrent? Well, that meant that all the forces had to pass through a single point. So this brings us back to our particle equilibrium. Remember how I promised we'd keep using all those things, all those ideas? Here we are. We're still doing concurrent force systems. So in this case, we'd have a force here, and maybe something like that, but in such a way that their line of actions, I've kind of put it in the middle of the word concurrent to help you remember, all pass through a common point. Now, when we do this, how many equations can we reasonably write? Well, it turns out you can only write 2. You can only look at some of the forces in the x and some of the forces in the y. Because if we did our moments about this point, it's not rotating. Some of the moments equal to 0 automatically. All the perpendicular distances are 0. So up here, where we didn't even need to write an equation, we just knew they were equal and opposite along the line of action. Here we've got 2 equations with 2 unknowns. So that's pretty good for us overall. Let's look at what that does to our structure over here. Here I've still got that moment happening in that fixed connection, so I don't really know what to do with that. So member ABC, probably not a three-force member. In fact, it's not a three-force member. It's just a multi-force member. Now, because of that, I can go ahead and finish off my free body diagram here for member ABC. And so down here, we said that we would have a force AY and a force AX and a moment at A because it's a fully fixed condition. Now, we do have something happening at C, so maybe I'll hold off on C for just a second. Because if I look at members C, D, E, how many locations are forces applied? Well, there's only 3 locations. Joint loads at C, joint loads at D, and applied load at E. So if I look at that, I can notice something. First off, which direction that applied load pointed? Gravity, so it's pointing down. It's the one thing I have to remember as a civil engineer. Gravity's pointing down like that, so there's my force at E. And what did we say about all the forces for a three-force member, which is what this is? What did we say? We said either all the forces are parallel. So I've drawn 2 forces on there already. I use my 2-force member to figure out the direction here for member FBD into joint D. So that's good. But is that parallel to force E? No, it's not. So if they're not all parallel, it means they have to all be concurrent. So it turns out that what I can do is I can extend my lines of action like so, and there's my point of concurrency. So all of my forces are going to have to fall through that line, including this joint force over at joint C. And so I can sketch it any old direction I want as long as it's along that line of action. So here I can say force C, and because I pulled the pin, I need to draw that force equal in magnitude, opposite direction over here on my vertical member, force C. So now I've got much simpler free body diagrams. How many unknowns do I have? Well, I've got force BD. It shows up in 4 different places on these diagrams. I got force FC. That's 2 unknowns. And then I have my unknown reactions down here, assuming, of course, that I know my weight. So I'm up to like 5 unknowns. But how many equations of equilibrium can I write for these 3 diagrams? Well, do I need an equation of equilibrium for my 2-force member? No, it didn't really do anything for me. I already know the FBD is equal to FBD. Surprise, right? Sum of the forces equal to 0. We're happy, nothing's moving. FBD is equal to FBD. Up here, though, how many equations of equilibrium can I write? Well, because it's a 3-force member and all forces are concurrent, I can only write 2 equations of equilibrium, sum of the forces in the x or sum of the forces in the y. I can go ahead and write a sum of the moment equation, maybe. I could do that. That's totally fine. But know that I'm never going to get more than 2 unique equations out of that. It's a beautiful thing. That's how the math works. So doing that, 2 equations, how many unknowns do I have? Well, I have 2 unknowns. Perfect. Everything I ever wanted in life. 2 unknowns. So right now I'm up to basically 1 diagram, 2 equations. 2 unknowns. When I add in this guy over here, I'm going to have 3 equations because it's a proper multi-force member. Anytime that moment shows up, multi-force all the way. You'll want to know that for an exam. Multi-force member there, 4 or more forces, moment couple there, acting on the member. And so I'm going to be able to write 3 equations, some of the forces in the x equal to 0, some of the forces in the y equal to 0, and some of the moments about some point, probably point A, so that forces FAX and FAY go to 0, their moment contributions. I just have that positive moment reaction there. But some of the moments is going to be equal to 0 as well. And so I now have 3 equations here. So 3 equations, 2 equations, got 5 equations. I said I had 5 unknowns. I can solve that system of equations. It's a beautiful thing. And because we knew what a 2-force member was and a 3-force member was, we were able to solve for this with 5 unknowns, 5 equations, rather than what we had before, which was 9 equations and 9 unknowns. Turns out if you take the time to solve those 9 equations and 9 unknowns, what you do is you prove the definition of a 2-force member and you prove the definition of a 3-force member. So you can totally do it that way. There's no problem. But if you can identify two force members and three force members from the get-go, you can really simplify your free body diagrams and simplify the number of equations of equilibrium you need to write. So that's two force and three force members. I look forward to seeing you in class.